In a very short time, we've already been able to send warming soaring. We're at 1.2, and unfortunately, we think we're going to reach 1.5 degrees very quickly by the early or mid-2030s at the rate we're going. All the climatologists have come together to tell the politicians, this is where we're headed, make the right decisions. There is no plan B.
Hello and welcome to this new show. Today we're going to talk about the climate, how it has changed throughout Earth's history, and especially how it's going to change from now on, particularly because of our impact. To answer all our questions, Gilles Ramstein is our guest. Hello, Gilles.
Hello.
So first, before we talk about the future and the climate in a few years, I would like us to go back over the earlier periods in Earth's history. We imagine the Earth as a frozen ball. We even talk about Snowball Earth. What was it like back then? Can we explain this concept a little bit?
Yes, actually the Earth is beautiful. Now, seen from a satellite, it's blue, it's ochre. Just imagining a frozen Earth is already a huge stretch of imagination. So actually, was the Earth frozen or completely frozen? What we call a snowball Earth in English. Well, yes, that's exactly what happened. Simply put, this is likely one of the most phenomenal discoveries of the late last century. That is to say, in the 1990s, we understood why and how, even though we had evidence since 1960. To keep it brief, people often talk about processes rather than the history of science, but here it's worth discussing the history of science. There was an English geologist named Harland who, in the 1960s, studied very large equatorial areas, territories that corresponded to the equator. At that time, he saw that there were plenty of tillites, which are signatures of ice caps. And so, since he was a very good geologist, he said that there were ice caps at the equator. But if there are ice caps at the equator, all other things being equal, that means maybe the Earth was a snowball. In the 1960s, there were two blocks, east and west. So, Harland turned to the best climate specialists of the time to understand. Whether it was from the east or west, they said, listen, my good man, imagine the Earth was entirely frozen. It would then be extremely reflective. That's what we call albedo, the reflective quality of ice. It reflects much more than oceans or continents. And so they told him, yes, you and I agree that today, as we talk here, just as in the 1960s, we're not standing in the snow. So we've come out of this glaciation state. To emerge from a frozen Earth, they explained to him that you would need such power that you basically had to multiply the solar energy by 1.5. And they explained to him that since our sun was a completely ordinary sun, we knew that the sun's brightness actually increased by 7% per billion years. And so they told him, you see, to deglaciate a snowball Earth, it would take about 1 to 2 billion years. But what you're telling me here, what you have as a record, dates back only 700 million years. So if what you're saying was true, we would still be in a snowball state. And Harland, who was a very good geologist, put that data aside. And we didn't really hear much about snowball Earth for a while until there were three among others. But in any case, I can, to simplify, tell you about three massive paradoxes that really brought this event back into the spotlight. So the first one was that, strangely enough, if you will, for a primitive Earth oceanographer, there's a kind of totem, which is what we call banded iron. In the primitive oceans, before there was oxygen, iron dissolved in a very different way in the ocean. And we had these very beautiful rocks called banded iron formations. And these rocks completely disappear. We don't have them anymore. Starting from 1.8 billion years ago, no more banded iron formations because the chemistry of the ocean changed. So there you go. During these glaciation episodes, about 700 million years ago, these snowball events, the last one was about 700 million years ago. Well, paleoceanographers find this type of rock as if the ocean was no longer oxygenated. So that's the first paradox. Why would the ocean no longer have been oxygenated at the time when these glaciations occurred? A second paradox is also that on Earth, this is a bit complicated, I'll try to make it simple, but on Earth, carbon exists mainly in two stable forms. Carbon-12 with 6 neutrons and 6 protons, and carbon-13, which has 1 more neutron. It turns out, and this is something absolutely extraordinary, that life, everything that is living, everything organic in its chemical reactions, has a preference for carbon-12. However, during these episodes, the ratio of carbon-12 to carbon-13 is not fractionated. It's exactly the same as what you have originally, at the level of volcanic fumaroles. It's as if all fractionation related to living things disappeared. That was the second paradox. And the third paradox, which was the most extraordinary, is that Haaland had clearly seen with his tillites that in the sediments you can see a layer of tillites. So a layer of sediments that are proof of glaciation. But above these sediments you find mountains of carbon, as if there was nothing else, as if it had formed carbonates, mountains of carbonate. So these paradoxes, they come one after another, all for that same period. And that's when there are two American researchers, one named Kirchfing and the other named Castini, who say, but you know, actually it wasn't the sun that thawed the earth, it was the same culprit again, it was CO2. So why CO2? So here you have to imagine, it's actually quite simple. You have a snowball earth. So it's freezing cold, but underneath the tectonics and volcanism stay the same. So the volcanoes emit CO2, just like when there isn't a snowball. Earth, volcanism emits CO2. The CO2 is released into the atmosphere. Today, the CO2 that's released into the atmosphere becomes part of the terrestrial biosphere, so it's trapped by life. But here, nothing. So the CO2 accumulates in the atmosphere. We're now well positioned to know that what happens when CO2 is stored in the atmosphere? Well, it causes warming. And what Kirchfing and Castini calculate is that with the current CO2 emission rate in a few million years, snowball Earth melts. That was an extraordinary result because it explained many things. It explained why snowball Earth had melted, so there was no longer the problem of waiting billions of years. In just a few million years, plate tectonics could do it. But what I haven't explained, and what's more important than anything, is that we understood, mainly thanks to work we did, but also work that other colleagues abroad did. But during those years, I had two extraordinary PhD students, one named Yannick Deladieu, the other named Guillaume Lehir, and we understood why there was this episode of Snowball Earth. So I explained to you why on Earth, even if it happens, it can't last long, but I haven't explained why it happened and why it happened 700 million years ago. And there's an excellent reason for that. So I'm going to explain that to you. It's actually really interesting. You should know that there are very important interactions between tectonics and climate on our little, truly extraordinary planet. So tectonics is the fact that the continents dance on the lithosphere. Over a human lifetime, we don't notice it at all. But on the geological scale of tens of millions of years, the continents dance on the lithosphere. They come together into supercontinents. The last one we knew was Pangaea, 250 million years ago, and then they disperse. And now we're in a phase of dispersion. We're about halfway through. The cycles last 500 million years. The last supercontinent, as I told you, was Pangaea, 250 million years ago. So in about 250 million years, there will be a single continent again. Very well. Now, because of this tectonic setting, the climate will change. Imagine if all your continents were in the polar regions. You'll say, oh, really, that's a setup. It'll be very cold, Mr. Ramstein. Yes, that's true. It'll be very cold. It's not only going to be very cold, but also very dry. The driest continent, when you ask people what is the largest desert on Earth, everyone answers the Sahara, except for glaciologists who answer Antarctica, and it's the glaciologists who are right. So if all the continents are in the polar zone, it's going to be freezing cold, but it won't rain. So you might say to me, okay, what's the connection? Well, that's very important because earlier we discussed what the source was. The source is volcanism. That's what emits CO2 into the atmosphere. And on a geological scale, for there to be a balance in the atmosphere, it's like a bathtub. You need a source, a faucet, and then a pump to get the water out. So the source is volcanism, but what is it on a geological scale that removes CO2 from the atmosphere? Well, if we've never heard of it, it's not so easy to imagine. It's what we call silicate weathering. So why is silicate weathering a sink for CO2? Because when it rains, the drops of water fall through the atmosphere, they pick up CO2, they fall on continental rocks, and they erode them. And when they erode them, there are chemical reactions, a chain of chemical reactions that will draw atmospheric CO2, reduce it to carbonate, bring it into the rivers, and the rivers will carry it to the sea. And that's the carbon cycle. The source is the volcanoes, and the sink is silicate weathering. So it creates a balance in the atmosphere. Why did I go on this long digression? It's because, let me continue, when all the continents are in polar positions, it's very cold. But it's very arid, so it doesn't rain. So the CO2 accumulates in the atmosphere. So it's not that cold because you have both the cold and the aridity. So it's like the drain is closed and the CO2 has accumulated. Now, conversely, imagine that all the continents are in an equatorial position. What will happen? Or tropical? It's going to be hot, that's true. It's going to be hot. But you know, these are also the most humid areas. It's going to be extremely humid. It's going to rain a lot. And as a result, a lot of atmospheric CO2 gets absorbed. So it's very hot, but it rains a lot, and the CO2 goes down. And that's exactly what happened 700 million years ago. There was a supercontinent called Rodinia. That's the one before. The landmass was called Rodinia. And it had a very particular characteristic because usually when it moves in any direction. But here, Rodinia was centered. It was a big continent centered on the equator. And it broke apart. It broke apart in the equatorial zone. And that's the most extraordinary configuration for drawing down a lot of CO2. Why do we draw down much more CO2 when the continents separate? Because each continental plate is small and gets thoroughly washed. Today, you know very well that the center of continents, for example, Australia, is very dry. And so 700 million years ago, we found ourselves in a very, very particular tectonic configuration where the continents were positioned in such a way that we were absorbing a huge amount of CO2, so much CO2, that we dropped below freezing temperatures and liquid water turned into ice. So now you know pretty much everything about the snowball. Why did we enter it? And why is a snowball unstable on Earth? Again, because of volcanism. And so for me, I've been working in this field for a long time. I'm 65 years old. It was undoubtedly a very important phase of my intellectual and scientific life because we felt like we were discovering things that weren't really known before. And what's the conclusion of that? It's still important. The conclusion of that is that when we have reliable data, we need to find a way to understand it. Some explanations are good, others are bad. The bad one was the sun, but it was the best we could have in the 60s. The good one was CO2, and this CO2 explanation, it explains the three paradoxes I told you about. Why? Because if you actually have a snowball Earth, the continents get covered with ice caps, like Greenland and Antarctica, but the oceans get covered with sea ice. Oxygen in the atmosphere can no longer reach the bottom of the oceans. The bottom of the oceans becomes anoxic, like in the primordial ocean, and we form BIFs again. When the Earth is almost completely frozen, there is no longer a carbon cycle, and carbon accumulates in the atmosphere. That's why there's no more carbon fractionation. And finally, why is it that after snowball Earth episodes, it's as if carbon is raining down? It's because the snowball Earth persists, CO2 rises, it reaches values on the order of a few percent of a bar, which means extremely high values. And then it's total meltdown. So the Earth thaws because of the greenhouse effect from CO2, but since there's a lot of CO2 in the atmosphere, it's going to take a long time to get rid of it. And so it's going to have to rain for a long time for the CO2 to accumulate at the bottom of the oceans and form what's called cap carbonates, mountains of carbonate. And so this explanation satisfied all three paradoxes I mentioned to you. But there were still a lot of debates. I would need much more time, but there were still two communities, it's like the Gauls, two communities that were really very resistant to this explanation. First, there were the glaciologists, because the glaciologists saw that, in fact, the end of a snowball wasn't a big meltdown, it happened in cycles. We explained that with one of my two PhD students. And then there were other people who weren't very happy, the biologists. That's for simple reasons I can explain. We're in a situation today where CO2 is rising rapidly. And you know, just like I do, that one of the consequences of having a lot of CO2 in the atmosphere is the acidification of the oceans. So you can imagine if a snowball melts in an atmosphere with much more CO2 than even during the Anthropocene, it's going to cause massive acidification of the ocean surface. So it's kind of contrary to the evolution of life. So biologists weren't really big fans of a snowball Earth. But we were able to explain, actually with a PhD student as well, that this way of thinking wasn't correct. In fact, the Earth was never completely covered in ice. Actually, for a very simple reason, there are always hotspots on Earth, so there are always areas that won't be frozen. These areas likely served as refuges for life. There is a lot of debate about Snowball Earth. It's still an area of research. Now, we know that there were 2 snowball episodes during the Neoproterozoic that are very asymmetrical. It's really always quite fascinating because there are lots of things we understand and lots of things we don't understand. But in any case, what you should remember from this is that yes, the Earth is beautiful, it's magnificent, it's blue and green, it has been white. But basically, compared to our neighbors, Mars, which is very cold, or Venus, which is extremely hot, the Earth has been very, very well regulated by these greenhouse gases. And there have indeed been a few accidents, but these accidents I just told you about lasted for several tens of millions of years. So it seems huge, but over the Earth's 4.6 billion year history, it's really just an accident.
All right. But so, if I understand correctly, CO2 tends to self-regulate because the hotter it gets, the more it rains. So more CO2 is captured, and the colder it gets, the less rain and water vapor there is. And so CO2 tends to go back up. So if I understand where you're going with this, we're supposed to have some kind of balance that's supposed to be maintained over time.
Exactly, you understood perfectly. The only thing to really understand compared to today is that this regulation between tectonics, climate, and CO2 happens over tens of millions of years. That is to say, people think when they know that continents drift, they say to themselves, well, it's normal for climates to change. Because, for example, today, if you drill in the Sahara, you'll find traces of ice from a very long time ago. Because indeed, that continent was once in a polar position a very long time ago. But that's a regulation. You're absolutely right. It's a regulation that works on a scale of tens of millions of years. Because actually, not only does tectonics move, meaning that the location of the continents determines what latitude they're at, it's hot, it's cold, but actually in a much less obvious way, actually the position of the continents, because of silicate weathering, is crucial for the CO2 sink. So actually, on exactly the geological scales you mentioned, it's the position of the continents that, through CO2, will regulate the Earth's climate. If the continents, the land masses, are too cold, there will be less rain, and so the CO2 will rise. If the land masses are at low latitude, so too hot, there will be a trapping of CO2. And that's actually what, over geological timescales, millions, tens of millions of years, causes the Darwinian evolution of life. Without these long-term regulations, things would be much harder. I don't know. I'm here with you today as the result of millions of years of evolution. Maybe it could have been different. But in any case, what is very clear is that this regulation, the fact that we don't go toward cold like Mars or toward heat like Venus, is very favorable to life. That's definitely a stroke of luck.
How can we measure temperatures so precisely over such colossal timescales? What are the techniques we can use to interpret the climate? Well, first of all,
there's a very important point in what you're telling me, which is how we measure temperatures. Today, we measure temperatures with a thermometer, with satellites, with rain gauges. We can measure extremely precisely and with excellent spatial resolution the distribution of temperatures. We have an absolutely extraordinary understanding of our climate. When you go back in time, for example, over just the last 2.5 million years, which we call the Quaternary, we can still say a lot of things. Going further back in time makes it harder. Remember one important date, the Cambrian explosion. 540 million years ago is when we finally start to find skeletons. So we'll be able to access biological material. Before that, before the Precambrian explosion, it's much more difficult because we no longer have any living specimens. But we have everything that's physicochemical. So earlier I talked to you in a somewhat caricatured way about carbon, but for oxygen, for carbon, for most of the elements in the periodic table, there are isotopes. And it turns out that this fractionation, the proportion of an element in its different isotopes. Let me give you an example. Oxygen is very important for us. 8 neutrons, 8 protons, oxygen 16. There is also very little, but there is some, oxygen 17, and there is a bit more oxygen 18 as well. Well, it turns out that this fractionation depends on many things, and as far as oxygen is concerned, it depends a lot on water, which is H2O. And thanks to isotopic fractionation, for example, from rocks, independently of life, we can determine temperatures. So, the further back in time we go, I'm telling you, the harder it gets. But for example, for Snowball Earth, for what we were looking at before, we have what we call proxies in the jargon. That is, these are kinds of changes that we can link to temperatures, which are very often related to isotopic imbalances. You might ask me how we can do this and how far back we can go. That's an interesting question because there are horizons. For each component, there are horizons. For example, ice is amazing, ice, because ice can do things that no continental or marine drilling can do. There are bubbles in the ice. So ice gives us the bubbles, the atmospheric composition, except that ice in Greenland, that's pretty much the time horizon. An ice core is about 150,000 years. In Antarctica, it's about 800,000 years, and we hope it'll be 1.5 million years. So the time horizon of the ice sheets is like the orange peel of Earth's history. So you might ask, Mr. Ramstein, what about the oceans? The oceans, between the time when the continental crust is formed and the time when it subducts, that's about 250 million years. So that's about, give or take, that's roughly the Jurassic period. Beyond that, it's the ocean floor's time horizon. Well, there are some specific things, but to put it simply, beyond that, all you have are the cratons, meaning the continental masses, which, as I told you, disperse and regroup. And there are only a few cratons that allow us to go very far back. There are some in Australia, some in Greenland, and so on. So obviously, the further back in time you go, the fewer markers you have. But the climate changes from certain events are so massive that, in fact, even if you're very nearsighted, you can still see them.
Have we already experienced major climate changes that are comparable to what we're experiencing today? I'm asking the question because, in fact, in the minds of many people, the climate changes we have today aren't so worrying since there have already been sudden changes in history. Are there similar cases in Earth's history that are somewhat like what we're experiencing today?
That's a good question. Analogies reassure people. It's comforting to think this has happened before and we got through it. So there are a lot of things that are quite problematic in this question. I'll try to explain them. We have a former president who said, well, the climate has always changed. He was right. I work on this. The climate on Earth has always changed. The toxic aspect in this context was making people believe that it has already happened. It's not a problem. Whereas in reality, there is no equivalent to what we're experiencing right now for very simple reasons. Nothing compares to this experience as humanity has never reached 8 billion before. So that's it, end of the story. Then you might say, okay, Mr. Einstein, there weren't 8 billion human beings, but have there been events that led to a big increase in CO2? So actually, if you look for, or there are people who say, have there been periods in Earth's history when we've had as much CO2? I'll answer this first question already. We're heading towards 430 parts per million of CO2. Is this extraordinary in the history of the Earth or not? Well, that's always a matter of time frame. If you're interested in the Quaternary, the last 2.5 million years, it's extraordinary. We haven't had 400 ppm during the entire Quaternary period. But outside the Quaternary, 3 million years ago, in the Pliocene. The Pliocene, 3 million years ago, isn't that distant tectonically compared to Earth's 4.6 billion year history. Well, back then, there were about 400 ppm. We know this thanks to reconstructions. So we're pretty sure that's about right. So what? Well, back then, it was about, on average, 2 degrees warmer. But it was in equilibrium. That means it wasn't a transitional climate. We didn't change the CO2 levels in 250 years. So it's not a good analog. You might then ask, what is the right analog? Unfortunately, the suddenness of climate change, not the fact that we're at 420, but the fact that in just 250 years, we've gone from 280 to 420. Well, events as sudden as this in Earth's climate history, as far as we know, there are almost none. Or when there are events that are comparable to major extinctions. So, the only real analog, and unfortunately, our biologist colleagues agree with us, is that when the climate changes this abruptly, the biosphere struggles to adapt. So at the same time, people talk to you about the sixth extinction, which is referenced by biologists. And climatologists talk to you about the suddenness of climate change. Still, for example, I work on a period that dates back 15 million years, the Middle Miocene. Why? Because climate modelers have been interested in the Pliocene, since it was similar to where we are today in terms of CO2. But by the end of the century, we think we'll be closer to 500 or even 1,000 ppm of CO2. So if you look at this single parameter, the most recent period when we had this level of carbon dioxide in the atmosphere was 15 million years ago. 15 million years ago is much earlier than 3 million years ago. So what? Well, back then it was about 6 degrees warmer. There was no Greenland ice sheet. There was just a smaller Antarctic ice sheet. So it makes you think about what could happen if we're no longer in a transitional phase like we are now, and we stay at 500 ppm for a long time. Well, Greenland is not made to exist in a world with 500 ppm today. By the way, that reminds me of something really important when it comes to moving toward climates that are closer to what we'll see in the future. The point is, what we're saying here about Greenland not being viable in the long term in an atmosphere with 500 ppm. I could explain to you how we know this, how the Greenland ice sheet formed, how the Antarctic ice sheet formed. It doesn't date back to Methuselah. It originates from specific periods. But now, with the sheer speed of climate change, we're threatening the very existence of these ice sheets. So Greenland is melting, but Greenland is a huge mass of ice. It has a lot of inertia, so obviously it's not going to melt overnight. But thanks to many instruments that are the result of human intelligence, we can measure not only how much water Greenland is losing, but also how much it contributes to sea level rise. And Greenland, for example, if all of Greenland were to melt, that would correspond to a sea level rise of 7 meters, okay? Over thousands of years, obviously, and assuming that we continue to have high CO2 levels.
So now I'm going to change the subject a little bit. Today we work a lot with tools to model the climate. Are we able to model the current climate reliably? How can we do that? Yes.
We are living in a time where the extraordinary intelligence of humans allows for extremely refined measurements of climate and weather thanks to satellites. And we also have huge machines and massive software that allow us to create what we call climate models. To calculate the climate, you need to perform calculations. It's fluid mechanics. There are two fluids that are heat carriers, meaning they allow the extra energy that arrives at the equator to be redistributed toward the higher latitudes. It's the atmosphere, which is very fast, that's weather, and the ocean, which is much slower. The coupling of the ocean and the atmosphere, along with a number of other features like atmospheric chemistry and the biosphere, makes it possible to calculate the climate. So today, we can calculate very precisely what is happening right now. But you might tell me that this doesn't prove anything, since anyway, the climate is changing today. The question isn't whether we're right at a given moment, it's whether we're able to predict climate change. You can't have proof that you predicted it correctly. That's impossible. On the other hand, you can say to yourself, hey, I'm going to use exactly the same models I used for the 21st century to study the past. There, I have data, I know what kind of climate changes happened, where they occurred, and I'm going to ask myself whether the models I use for projections are at least able to calculate past climate changes. So that's really the focus of my life, but also of many other colleagues, and we've done what we call model intercomparison exercises. There are two French models, Météo France and IPSL, as well as English and German models. All these people got together around a table. We distributed just one set of boundary conditions so that everyone would do exactly the same thing, and we checked to see if we could do it. Well, yes, we are able to reproduce, not everything. There are plenty of things we can't reproduce. But the evolution of climates over relatively long time scales and for relatively specific periods. Yes, we are able to show that our models are capable of reproducing past climate changes. Not with the precision we would like. There are certainly some missing processes, but basically, yes, we do it. So that's interesting, but it's even more interesting because climate change, is happening incredibly fast. The question is, are we able to reproduce because we are in the midst of climate change? Are we able to reproduce, to understand, and to reproduce it? The fact that since 1750 the global temperature has increased by 1.2 degrees, are we able to reproduce that? Also, The fact that we've warmed more in the polar regions than in the equatorial regions, are we able to reproduce the fact that the global sea level has risen by 20 centimeters using models? Since the change is ongoing, are we at least able to show that? Well, yes, we are able to show that. We are able to show much more than that. We are able to show that there is no plan B. That means there is no other scenario except for anthropogenic changes, meaning that humans, through their development, have become, like tectonics, if you will, a forcing factor on much shorter time scales, a driver of climate change. So humans, through their development, are able to send things into the thin layer of the atmosphere to modify it. Few species in Earth's history, I personally know of only one other species that did this, and that's cyanobacteria during the Great Oxidation event. The key difference with cyanobacteria is we know what we're doing. So right now, we are very quickly changing the composition of our atmosphere, unfortunately with greenhouse gases, which are the result of burning fossil fuels. And because we're burning record amounts of fossil fuels, we're seriously disrupting the climate. Well, when we take that into account, when we also consider that we're changing land cover, and we take into account a number of human-induced changes, we're able to simulate very accurately how the climate has changed since around 1750. If you look, for example, at the latest report for policymakers, the summary for policymakers from Working Group 1 of the IPCC, that's the group I work in, you'll see the first figure shows you that we match the data relatively well. By taking into account all aspects of what we call anthropogenic forcing, meaning the fact that human societies are expanding and emitting greenhouse gases. We've talked a lot about CO2, but there's also methane, N2O. There's also land use. The fact that we change the land surface, so we change the hydrology, we change the albedo, we change the aerosols. When we take all that into account, we can reproduce it very well. And not only can we reproduce it very well, but there is no other physical process that could explain it. That's really what's important, because there are people who told you, who said at the beginning of the Anthropocene, oh, no, that's sunspots, but that never held up from the start. So here we are, now today, in a world that is changing. We are able to document this change, the speed of this change, with extraordinary spatial detail, and we are able to explain it. The only thing we might not be able to do is change the trajectory.
What I find interesting, and I'll come back to this point a little, is that today there are many people who sometimes point out that the climate has started to change a little bit. Before the more industrial era, we released much more CO2. You mentioned an interesting point. It's not just about CO2, but also how we treat the soil and our overall impact. What are all the factors that we as humans can control which contribute to changing the climate?
That's also a very interesting question. You know, actually, the people we call denialists work with simple ideas. The simple idea is to say, for example, first, the climate has always changed, okay? We just saw that the climate has always changed, but it's a mix of time horizons. Now it's changing with 8 billion people, 10 million, and soon more, in times that are really extremely short. Another idea is to say, oh no, but you're not going to make us believe that CO2, which is measured in parts per million, is capable of causing such upheaval. Of course it can. We are able to show that the radiative balance of a gas that has almost doubled, methane for example, has doubled, will have a very strong warming effect. Another idea is to say, oh no, but okay, we're changing the climate. Well, that's already a point for us, but this has already happened before. And besides, if we look, it's not synchronized. It's completely synchronized, meaning that the massive climate change we see is dated to the pre-industrial era. So you might say to me, but before that, and actually, this was an interesting debate from a physicist, a scientist I like named Rudiman, who said, in fact, at trace levels, you can see this climate change and the hand of man much earlier. So why did Rudiman say that? He said it because we started deforesting well before the pre-industrial era. We were able to create rice paddies, to use wetlands long before the industrial age, and that, perhaps in a very small way, but still in a small way, we did. Human influence is visible earlier, but in a striking way, it has really been visible since the Industrial Revolution. Here's something interesting. Check out the summary for policymakers from IPCC's Working Group 1, which I already mentioned. You look at the last figure, and there you see something. It's very simple. It's a figure where on the x-axis, that is, at the bottom, you have the accumulation of greenhouse gases, and at the top, you have the temperature increase. And you see that the temperature increase we're experiencing, that is the fact that now we're at 1.2 degrees Celsius compared to 1850-1900, already 1.2 degrees Celsius of warming. It is directly proportional to the accumulation of greenhouse gases in the atmosphere. That means the more we put in, the more it heats up. It's very simple. And since we can't remove it, it accumulates in there. So actually, if we want to stop the warming, there's only one thing to do, which is to burn less fossil fuel. It's just mathematics. And another thing that happens with climate skeptics is that they say, yes, you're telling us this, but you know, there was also the medieval warm period when it was a bit warmer, and then there was the little ice age when it was a bit colder. That's absolutely true. Fortunately, the climate keeps us from being bored on Earth. Each year is different. Things change every year. So if we look at it, and we can look at it precisely, this was actually the subject of a book by Leroy Ladurie, a historian who, using historical data, recreated the climate of the last 1,000 years. It was still mainly focused on the Northern Hemisphere. Since then, we've done planetary reconstructions. And indeed, over the last 1,000 or 2,000 years, there have been fluctuations. These global scale fluctuations correspond to 0.1, 0.2, 0.3 degrees, so they're very small compared to what we're currently producing. Once again, denialists want us to believe everything we're experiencing is completely normal. They forget to mention that this is 10 times less significant over several hundred years, because the medieval warm period lasted quite a long time, and so did the Little Ice Age. We, in a very short time, have already managed to shatter the warming record, and we're at 1.2, and unfortunately, you must have heard about it. But we think we're going to reach 1.5 degrees very quickly in the early or mid-2030s at the rate we're going.
So, according to the models we have and the way we're changing or not changing society, what do the predictions say about the coming years strictly in climate terms?
Yes, so for that, I want to pay tribute right away. Me, I'm just a researcher in paleoclimate, basically. Everything I'm telling you here is thanks to hundreds, thousands of people who work on models that are still extraordinarily complicated, we do numerical simulations on big computers, storing data, that's it. All this work is highly collaborative. It's not at all the work of a single person. I really benefit from the evolution of the models, from what engineers and physicists have been able to put into these increasingly precise models to try to reproduce reality as accurately as possible. One really extraordinary thing in climatology is the fact that quite early on, in the previous century, in the 1950s and 60s, there were people who understood what was going to happen and who said, well, what's important is to be able to make projections to see where we're headed, depending on different scenarios. So we started to make large atmospheric models because that's the fastest way heat is transported. And then that was in the 1960s to 1980s. After that, we coupled these models with global ocean models. Then we added atmospheric chemistry. Then we included the continental and marine biosphere. And we made bigger and bigger models. So they became more and more resource intensive and increasingly precise. And the next thing is that once you have these large models, you have to project them according to different scenarios, since it's the future and you don't know what will happen. So people have organize themselves to use many different models with the same scenarios to see which characteristics were robust. And it's thanks to this that the IPCC was structured, meaning that for the first time, I don't think there's any scientific equivalent at the global level. All the climatologists came together to create, about every 6 years, an overview of the state of the art. And why? To try to tell politicians, the people in power, this is where we're heading, make the right decisions. For that, we established several scenarios. There are scenarios where we get it under control, meaning we emit fewer greenhouse gases from fossil fuels, and scenarios where we don't manage. We'll emit more, and based on these scenarios, we'll see where that takes us by century's end. That's basically the main work of the IPCC. The latest, the 6th IPCC report, dates from 2023. It's thousands of pages, but I encourage all the listeners. It's a bit tedious because it's interrupted by lots of statistics. But read the 30-page summary. The summary for policymakers for Working Group 1 is relatively accessible, and it gives you pretty much the state of the art today on these issues. And so, yes, we are able to project with relatively good reliability what the Earth will be like in 2050 or even in 2100. Also with the quantification of uncertainties.
So then, what would be the impacts, at least in the short term, over the next few decades, for example, on sea level, on temperatures, on biodiversity?
So I'll answer your first two questions. For the third one, you'll need to find someone else. I'm not a biologist. So regarding sea level, it's very interesting. Why is the sea rising? If we were dinosaurs and we had all bought cars and we burned fossil fuels, there's one thing that wouldn't have changed, and that's the fact that a water molecule, when it's heated, takes up more space. That's what we call thermal expansion. As we heat the oceans, the water molecules in the oceans expand, they take up more space. And that explains most of the signal and the 20 centimeters I mentioned to you. Thermal expansion, it's the same thing for dinosaurs and for humans. La différence, sans doute, elle vient du fait que on Earth, as we conduct this global Anthropocene experiment and humans show they can alter the atmosphere, what is our current climate context? We're in a context where there are ice caps. It's rather a cold period in Earth's history. We have two ice sheets, Greenland and Antarctica. And it's in this context that we're conducting these experiments. And unfortunately, because of polar amplification, when you say that the global temperature on Earth is going to rise, for example, in a few years, in a few decades, by 2 degrees. Overall, that doesn't reflect the fact that at the equator it will be about 0.5, but at the pole it will be more like 8 or 10. That's what we call polar amplification. We're warming overall, even more at high latitudes where the ice caps are. From the listener's point of view, it's important for them to understand that of the 20 centimeters today, the main factor is thermal expansion, but it's now being closely followed by two other contributors. One that is a minor contributor, even though it's significant in the short term, is the glaciers. If you look at satellite images of the Earth, you can see that tropical glaciers are disappearing before our eyes. But if all the glaciers of the world, joined forces to melt at the same time, well, that would be a few dozen centimeters. If the Greenland ice sheet melts, that's 7 meters. The Antarctic one is 58 meters. So you see, these are not the same volumes. They're also not the same time scales. As I said, you can see tropical glaciers disappearing with the naked eye. The Greenland ice sheet is losing mass, but it's losing only a small amount compared to the total mass of water that's in the form of ice sheets in Greenland and Antarctica. By the way, people don't really know this because it's not obvious, but the main reservoirs of fresh water on Earth are those two ice sheets. That's about 60% of the freshwater reservoir we have on Earth.
I might be saying something silly, but from what I understand, it's supposed to be a good thing if the ice sheets melt, because the more water there is, the more it allows the Earth to absorb CO2. Isn't that exactly what will help regulate the cycle and bring CO2 levels back down to normal? No.
It's not silly, it's just a bit of a distorted view of things. Why? We live in a world where sea levels are rising noticeably. We think that if we manage things poorly, sea levels could rise by at least 1 meter. There are several aspects to this. Look at the distribution of populations on Earth. There are a lot of big cities and populations living at sea level. So when you raise the sea level relatively quickly, since the last deglaciation, 30,000 years ago, when sea levels rose by 120 meters in 10,000 years, there weren't many people at that time. Now there is a huge population living at sea level. So when you raise the sea level, you're going to have unimaginable migrations, unimaginable human problems. So what you're saying is that on a planet that isn't populated by humans, you could say it's not so bad. There will be some feedback between the fact that and that's what des océans. Alors juste pour vous dire, that's what's important. That's what's important. En fait, quand vous quantifiez les choses, that's what's important. Enough. To have an ice cap, it's very simple. It's like a bathtub. And there's accumulation, what falls on the ice cap, and ablation, what melts off it. When you raise your CO2 too much, ablation far outweighs accumulation. So you're going to lose mass. And despite the feedback you're going to talk about, you won't be able to prevent it. You won't be able to stop the Greenland ice cap from continuing to lose. So actually, what we've started now with the Anthropocene, you might say, well, after all, humans are crazy. They're going to burn all the fossil fuels. But since there's a finite amount of fossil fuels, let's say that in at most 500 years, they'll have used up the oil, gas, and coal. That's absolutely true. But the effect won't just last a few hundred years, because once you've started the process of melting the ice caps, that's something that will continue for thousands of years. We're on another level.
There is inertia?
That's right. There's inertia, which is actually good for us. These ice caps have inertia. To say that in the suddenness of change, the time it takes for it to seep into the ice and make it melt, it will take, fortunately for us, hundreds or even thousands of years. And that, despite the fact that you will be adding fresh water, creates a lot of other problems that I could come back to about the ocean dynamics, because it also has impacts on ocean dynamics, the fact of melting the ice caps, because it adds fresh water in areas that are quite sensitive. But regardless of that, the feedback phenomenon you mentioned, more absorption, more ocean surface, won't stop the ice caps from melting. And about temperatures, so you also mentioned to me, I mainly talked about sea level rise, but when it comes to temperatures, that's a big question. That is to say, thanks to the model, we can know not only, depending on the scenarios, by how much the temperature will increase by the end of the century. That's one thing, and also how it will be distributed. It's not just the temperatures, but also the precipitation. For example, all the models agree that the Mediterranean basin will warm up a lot, but also become much more arid, and quite quickly. So if you will, actually, people like me, but especially those who work on future climates, actually, they shine a spotlight on the risk, actually. Those that are very likely to happen. And from there, we have to make decisions to prevent that. In my opinion, that's really the main question. How do we do it, and why haven't we managed, even though we've known this for 30 years, to really make things change? Everything I'm saying here proves that, in fact, greenhouse gases have protected us. They protected us. And for a very long time, the climate was regulated thanks to CO2. And now we're disrupting the system in such a way that it's not going to protect us at all. And I would still like to say, to finish, well, to say a word about the fact that we shouldn't be too pessimistic. The thing is, well, my point is that humans have a big brain. They are extraordinarily intelligent. They are extremely well informed. So now the question is, do we change our energy trajectory? That is, do we stop developing with fossil fuels or not? That's a question, you could say it's a question of intelligence. It's a bit silly because, in fact, if that were the case, we would have already changed. So it's not just intelligence, there's also certainly the power of lobbies. It's no accident that Trump came to power in that context. It's not a done deal. I mean, just because we know, just because we're well informed, doesn't mean we'll be able to change.
Also, a lot of people are quite pessimistic about these issues. They think that even if we stopped everything now, actually, the chain of events would still play out to the end. It would still keep going.
No, because every 1/10 of a degree counts. So if you stop everything now, it will be much, much less bad than if you stop everything in 50 years. If you want, it's like a domino effect. Avec une espèce of amplification that gets even more serious. It's something I often talk about. You arrive at a lock with your boat. If you haven't turned the wheel to align with the lock, you're not positioned correctly. If you wait until you're right in front of the lock to crank the wheel, it's already too late because the boat has inertia. That's our current situation. We know where the lock is. We know we're going into the lock. The question is, are we going to turn the wheel to avoid going through the lock, but with 2 billion people surviving instead of 8 billion? That's the real question in the end.
You also wrote 2 books, the first one called Journey Through the Climates of the Earth. So what is this book about?
So actually, this book is the result of a suggestion from Jacob to write a book about climate. I did some research and saw that there are already some very good books about climate. First I thought, but what can I bring to the table? And then I had this completely crazy project that took me 3 years of weekends to make a book about the history of climate from the very beginning to the end being billions of years from now as well. It starts, and this story will also come to an end. So why? If I say this project was a bit crazy, it's because, well, as you know, the Earth is 4.6 billion years old, but we can say relevant things about the climate starting from about 3 billion years ago. Before that, it was very difficult. And relevant things about the climate in the future, from the point of view of major evolutions, major processes like photosynthesis, the disappearance of continents, we can also go a few billion years ahead. Beyond what we're currently experiencing, knowing that the ultimate end is when the provider of our energy, that is the sun, transforms into a red giant, which will happen in about 10 billion years. That's the physical end. We get burned. But before that, life will have disappeared long before. So I started this book in a very naive way. And actually, as I was writing this book, it's a bit like Penelope, you know. You're documenting Earth's climate history over billions of years. And every 2 weeks, journals like Nature or Science question parts of your work. So it's endless, actually. Didier Jacob told me, Mr. Ramstein, your book should be published now with COP20 in Paris. This is the perfect time. They then gave me 3 months to finish. So at that point, I can tell you that I did what needed to be done. I had already worked a lot. And so the goal of this book was to explain to people how ultimately, when we look at the Earth, we say to ourselves, it's really amazing, we're here. That it's no accident that the Earth isn't a ball of ice, that the Earth isn't an oven like Venus whose surface is at 400 degrees. What is it in the end that has made it so we've never lost our oceans, that life could develop, that there was never a time that was too hot, too cold, or too dry overall that would have really dealt a blow to biodiversity? So that was the subject of this first book.
All right, and so you wrote a second one, which is a bit simpler, a bit more accessible, because from what I understand, the first book you wrote is a bit more technical. So the second book is The Climate in 100 Questions. So what is it then?
The first book, when I conceived it, I really made it so that people would understand. All Science and Vi readers can read this book without any issues. On the other hand, if you talk with people in the street, actually, I had participated. In fact, I was even one of the initiators with other colleagues in a master's program to train journalists on climate change called Climate and Media. And while doing this M2, this course, I worked with a journalist since we were working. This master's program was designed together with a journalist, since it's about training journalists, whose name was Sylvester Hewitt. And so in that case, it's a bit different. I think Talendier approached Gilles, who's much more well-known than me, to do this book. Jean said, well, no, I have a lot of things to do. Ask Gilles. And I said, well, I'll take it. Because I was very interested in people on the RER. It's 100 questions about the climate, so there are 100 questions, and about half of it is really scientific, and the other half is more Sylvester's part. It's more about how current climate change affects society. We each wrote, exchanged drafts, and the result is this co-authored book. Now, this one, on the other hand, is very accessible. You can read it in any order you want. There are 100 questions, but if you start with number 67, there's no problem at all. And then read number 2 afterwards, there's no problem. And that's really something you can do. The question is just a few words, obviously, and the answer takes up about 45 pages, which is already huge. 100 climate questions make it a small yet thick book. And it's from Talendia in 2021.
All right, so did you write this all by yourself, or did you co-write it with someone else?
It's a book written by 4 hands and 2 brains. That means we first discussed the questions a lot, also with the editor, and then when we agreed on the 100 questions, basically, I'm exaggerating a bit. I wrote the foundation for the first 50, which are more related to my expertise as a climatologist. And Sylvester Hewitt, who has been a science journalist for a very long time, but who has specialized in climate. By the way, after this book, he wrote another book, Talendia, about the IPCC, to make it accessible to everyone. And so afterwards, we exchanged our drafts. Because we both have strong personalities, things sometimes got heated when trying to agree. Afterwards, we wrote the conclusion and the introduction together, so it's really a book co-written by both of us, but with the same idea that we both shared, which was to make it accessible to the widest audience. And why do I say that? I told you the trajectory is what matters. So there are 2 options. Either you are in a non-democratic system with people who think they are in power forever and who have long-term plans. You don't see which country I'm talking about, China, and indeed they have long-term plans. They did what was necessary to take control of wind and solar power, and they know how to build nuclear power plants. Or you want it to still be a democratic country, and in that case your only solution, it's necessary but not sufficient, is that people understand what is going to happen to them. The young people who are 25 years old today in the 21st century, who are going to live through this century, they will face really serious problems where they will have to think carefully and make the right decisions. And the only small contribution that Sylvester and I can make is to give them a bit, I don't really like this expression, but still, to give them the tools to understand the world they are going to live in. Because otherwise, if you don't do that, if citizens don't understand anything about what's happening to them, it opens the door to a lot of things that I think neither you nor I want.
In any case, we'll put both books in the video description for anyone who's interested. I think there will be a lot of them. We're coming to the end of our interview, so thank you very much, Gilles, for the time we've spent together. It was extremely interesting.
Thank you as well for inviting me.